Hi, today in this session we are going to discuss about the topic particle in an infinite potential well. So, particle in an infinite potential well. Here, consider a particle of mass m which is moving back and forth between the walls of a one-dimensional box and separated by a distance a. Suppose if we take a particle which is in the box. So we are considering a particle. So this particle's mass is m. So m mass of a particle is moving back and forth between the walls of one dimensional, and it is separated by a distance a. So the box distance is x is equals to 0 to x is equals to a. Suppose that particle is a free electron and it is trapped in a metal or charge carriers trapped by potential barriers in an infinite potential well. Suppose this particle may be a free electron and it is trapped in a metal or charge carriers trapped by a potential barriers in an infinite potential well. So later the particle travel only the x-axis and it is confined between x is equals to 0 and x is equals to a. So this particle is confined here between x is equals to 0 to x is equals to a by two infinite hard walls. So two infinite hard walls so that the particle doesn't have chance to penetrate them. That is, the particle has no chance to penetrate the walls. Okay, as the particle is moving back and forth, that is, it is confined between x is equals to 0 to x is equals to a between the hard walls so that there is no chance to penetrate with the walls because that is two hard potential walls. So this is the diagram of particle in one dimensional box, that is infinite potential well, particle in a infinite potential well. So this is the wall. So at the walls the potential is infinity, infinite potential well. So it is separated with a distance x is equals to 0 to x is equals to a. X is equals to 0 to x is equals to a. And inside the wall, the particle is moving back and forth so that we are saying the particle is confined between the hard infinite potential well x is equals to 0 to x is equals to a. So inside the potential wall, that is inside the potential well, v of x is equals to 0, where outside the potential well, it is equals to infinity. So it does not lose energy when it collides with the walls and its total energy remains constant. So as the walls are very hard, so infinite potential well, So the particle is confined between the hard walls, so there is no chance to penetrate them. So it does not lose energy when it collides with the walls, and its total energy remains constant inside the box. So this box can be represented by a potential box of width, a uh, the potential walls of infinite height at x is equals to 0 to x is equals to a, so that the potential energy v of the particle is infinitely high on both sides of the box, and inside it v is uniform. So outside the box, the potential energy is high, but inside the potential box, the potential energy is uniform. That is that here in this diagram, if we take the regions as 1, 2, and 3, so there is this is x is less than 0. So x is less than 0 region. So x is greater than a region. So inside the potential box, that is inside the potential box means that in this region, so in this region, you can say that x is greater than 0 and x is less than a. Okay, here inside the potential box, this potential energy is constant. This potential energy is constant. But outside the walls, that is x is less than 0 and x is greater than a, the potential energy is high, that is infinity. That is infinity. So, so v of x is equals to infinity when x is less than 0. So potential energy V of x is equals to 0 inside the potential well. So the potential well width is 0 to a width. And outside x is less than 0. Here x is greater than a. So here it is infinity. V of x is infinity. So v of x is equals to infinity means that x is less than a. So here it x is less than a. So the potential energy v is infinity. So when taking v of x is equals to 0, so inside the potential box it is 0. So what is the region here? 0, x is less than equals to 0, x is, x is greater than equals to 0, and x is less than equals to a. This region, V of x is equals to 0. Potential energy is 0, uniform. And x is equals to a. So the potential V of x is equals to infinity if x is greater than a. So here it is infinity. So thus the wave function psi of x, the wave function psi of x of the particle in the region 0 is less than x less than a, where v is equals to 0, it is described by the Schrodinger's wave equation in one-dimensional case. So the Schrodinger's time independent equation which we derived in the previous session, dou square psi by dou x square plus 2m e minus v by h cross square psi is equals to 0. So the wave function psi of x of the particle which is in the region 0 is less than x less than a, that is where the potential energy is 0 of the particle. So inside the potential box, the wave function psi of x So then the Schrodinger wave equation, we are taking Schrodinger's wave equation in the case of one dimensional. So that Schrodinger's wave equation is, that is Schrodinger's one dimensional wave equation is dou square psi by dou x square plus 2m into e minus p by h cross square psi is equals to 0. But here inside the potential well, inside the potential well, so that is inside the potential well means that here um, x is equals to 0, x is equals to a, v of x is equals to 0. So that here in this case, inside the potential well, v is equals to 0. So that v is equals to 0. Let's substitute v is equals to 0 as it is, as the particle is inside the region. So that is 0 is less than x less than a. So that v is equals to 0. Let's substitute v is equals to 0. Dou square psi by dou x square, dou x square is plus 2m e minus v by h cross square psi is equals to 0. So dou square psi by dou x square plus 2m e minus 0 by h cross square psi is equals to 0. So that dou square psi by dou x square plus 2m e by h cross square into psi is equals to 0. So here in this case, I am taking the term 2me by h cross square is k square. So that let's substituting instead of 2me by h cross square, k square. So k square psi is equals to 0. As k is equals to root of 2me by h cross square. So this implies k square becomes k square becomes 2me by h cross square. Okay, so let it is equation 1. So the solution of this equation 1, the solution for this equation 1 is psi of x is equals to a sin kx plus b cos kx. Psi of x is equals to a sin kx plus b cos kx. So here where a and b are the arbitrary constants. A and b are arbitrary constants. So now applying the first boundary condition. What is the first boundary condition? X is equals to 0. First boundary condition is x is equals to 0. The second boundary condition is x is equals to a. So that is, it has two boundaries, x is equals to 0 and x is equals to a. So applying this first boundary condition, so the expression will become, so applying first boundary condition, that is x is equals to 0, then what will be the psi of x? Psi of x is equals to 0. Psi of x is equals to 0. So that psi of x is equals to a sin kx plus b cos kx. This is the solution for the de Broglie's one-dimensional wave equations in our derivation. So here, so the solution for this equation 1 is psi of x is equals to a sin kx plus b cos kx, which is equation 2. So that psi of x is 0 and a sin kx. So a sin k into 0. So 0 sin 0 is 0 plus b cos k into 0. So 0 is equals to Sine 0, 0 plus b cos 0. b cos 0 is 1. So that b is equals to 0. So by applying the first boundary conditions to the equation 2, we'll get b is equals to 0. Now we are going to substitute the second boundary condition. So the second boundary condition is x is equals to a. X is equals to a. So when x is equals to a, psi of x is equals to psi of a. So that is equals to 0. So that psi of a is equals to a sine kx. So actually we are going to substitute in the second equation. So second equation is this one. Psi of x is equals to a sine kx plus b cos kx. So applying in that, so psi of x is psi of a. So psi of a is equals to a sine ka plus b cos ka. That psi of a is equals to a sine ka plus b cos b is 0 here. So that b 0 into cos k is 0. So implies psi of a is 0. 0 is equals to a sine ka. So here in this equation, a sine ka is equals to 0. Either a may be 0 or sine ka be 0. So here in this expression, either a becomes 0 or else sine ka becomes 0. Both cannot be 0. Both the a and sine ka cannot be 0. So a is not equals to 0. If a is equals to 0, then psi becomes 0. If a becomes 0, then psi becomes 0. So that there will be no solution. So there will not be any solution if a is equals to 0. So this means the particle is not in the well. The particle is not in the well. So that to satisfy this one, we are taking sine ka is equals to 0. Sine ka is equals to 0. So sine ka is equals to 0. Ka is equals to n pi. K is equals to n pi. So k is equals to n pi by k is equals to n pi by a. So where n is equals to 1, 2, 3 and so on, and we cannot take here n as 0. So here we are taking n is equals to from 1, 2, 3 onwards, but it cannot be 0. So as if we take n is equals to 0, k becomes 0. If k becomes 0, energy becomes 0, E becomes 0, and hence psi of x is equals to 0 everywhere in the box. So the particle with 0 energy, cannot be present in the box. Particle with 0 energy cannot be present in the box. That is, particle in the box cannot have 0 energy. That is, particle cannot be have 0 energy. So the wave function for the motion of the particle in the region 0 is less than a, 0 is less than x less than a, or given by simplifying the second equation, sin of x is equals to a sin kx, sin of x is equals to a sin of n pi by a into x, as k is equals to n pi by a, which we got in the previous one. Here k is equals to n pi by a. So here the solution of this one is a sin kx. Here also So here Ka is equals to 0. So here K is equals to n pi by A. So here when n is equals to 0, K becomes 0, when E is equals to 0. So no energy with 0 couldn't be present in the region which is 0 is less than x less than A. So particle in the box cannot have 0 energy. So that the wave function for the motion of the particle in the region 0 is less than x less than A or given by simplifying equation 2. So sin of x is equals to A sin kx. So what is the second equation? Psi of A is equals to A sin k. So second equation means psi of A is equals to A sin k. So that is psi of x is equals to A sin kx. A sin kx. So simplifying this equation. So for n particles, the wave function sin of x is equals to A sin k. K is n pi by A into x. So this is the wave function. This is the wave function of a particle which is inside the potential well. Which is inside the potential well. So um, first in this topic, first we have taken a particle. So let it be free electron. So this free electron is trapped in a metal. So it has some charge. So potential, at least it is trapped in the potential barriers in a infinite potential well. And the particle is moving along x-axis through and fro in between 0 and A. So that there is no chance to the particle to escape from the potential well because of hard walls. So that inside the potential well, the potential energy is uniform. Outside the potential well, the potential energy is infinite. So in this case, we are taking three different so two different regions we are getting. So that is for v of x is equals to 0 and v of x is equals to infinity. So v of x is equals to 0 inside the potential well, v of x is equals to infinity outside the potential well. So in this case, we are going to uh, deriving, we are going to simplifying equations for both the regions of potential energy, potential energies of a particle. So that we are taking Schrodinger's one-dimensional wave equations in this case. So by taking the one-dimensional wave equations of a Schrodinger, so dou square psi by dou x square plus 2me minus v by h cross square into psi is equals to 0, where we are taking the first region, so that is particle inside the potential well, so that v becomes 0. So substituting v is equals to 0, so we'll get dou square psi by dou x square plus 2me by h cross square into psi is equals to 0. But here taking 2me by h cross square is equals to k square. So that we'll get dou square psi by dou x square plus k square psi is equals to 0. By simplifying this expression, we'll get the solution psi of x is equals to a sin kx plus b cos kx. So here a and b are the arbitrary constants. A and b are the arbitrary constants. So in this expression, we are going to substitute the two regions, that is uh, two regions that is we are taking two boundary conditions. That two boundary conditions, one is at x is equals to 0 and another one is x is equals to a. Okay, so x is equals to 0 and x is equals to a. So if we take x is equals to 0, psi of x is equals to 0. So substituting here, psi of x is equals to a sin kx plus b cos kx. So when substituting the first boundary condition, so b becomes 0. Then applying the second boundary condition, that is x is equals to a. So psi of x is equals to psi of a is equals to 0. So in this case, we'll get the value expression 0 is equals to a sin kx. Here two cases are there. One is a may become 0 or sin ka becomes 0. If a is 0, if a is 0, then that is a and b both wouldn't be 0. If a is 0, if a is 0, we don't get the any solution for that. So a is not equals to 0. So here we are taking sin ka is equals to 0. A sin ka is equals to 0. So that sin ka is equals to 0, that is equals to ka is equals to n pi. So that k is equals to n pi by a. So here we got the value of k. K is equals to n pi by a. So here where n is 1, 2, 3 and so on, and n is not equals to, sorry, n is not equal to, we cannot take n is equals to 0. We cannot take n is equals to 0. If we take n is equals to 0, energy becomes 0. So that 0 energy inside the potential well does not exist. So that n is equals to 1, 2, 3 and so on. So the wave function of the particle which is moving inside the potential well is psi n of x is equals to a sin kx. So psi n of x is equals to a sin of k is n pi by a. So n pi x by a. This is the wave function which is the particle moving inside the potential well. Okay, so in the next session we are going to discuss about the eigenvalues of energy and their eigenfunctions of a wave associated with a particle. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.